Hello and welcome, wonderful calculus students from all over the world, all 6 of you who are going to watch this. But anyways, this is a very strange way to do a video. I'm not stupid. I realize this is very weird. I'm just recording my screen, talking over it, and then I'm going to upload that. That is not usually how you go through notes. I am not oblivious to that fact, but hey, that's what we got. That's what we're going to try to do. I am sorry if this is not ideal, but this is what I got, and hopefully I can still offer some good insight despite the strange formatting. So, we are going to be going over sequences and series today, more specifically, testing convergence of p-series and other series using the limit comparison test and the direct comparison test. Now, I ask that if you're watching this video, you should have basic knowledges of sequences and series. You should know just arithmetic and geometric, all that good stuff. And you should know what makes a geometric diverge, what makes it converge. If you don't know that, I highly recommend that you learn that first, and then you come back to this video. It'll be much more beneficial if you know that. So we're going to jump right in with p-series. What makes a p-series? What is a p-series, and what makes it converge? Well, this is a very, very simple thing. All right, so a p-series is defined as the summation of 1 over n to the p, where p is a constant. It's very simple. I mean, p cannot equal 1, and p must be greater than 0. That's the only restrictions on p. It's written right there. But aside from that, p could be anything. And this is literally like the most simple test ever. If p is greater than 1, it converges. If p is less than 1, it diverges. It doesn't matter if p was 5 million, it would still converge. It wouldn't matter if p was 0.000000001, it would still diverge. So this is a very simple test. There's a little proof I have written down here that we wrote in our notes. I'm not going to go through that. It's an easy rule to remember, so I don't feel the need to explain the proof. So let's just go through a few examples. You have the summation of 1 over n to the 5. Side note, before I go into this problem, as you can see, I didn't write any limits. Or like, what I mean is I didn't write the summation from n equals 1 to infinity. I didn't write that. If I didn't write any kind of limit like that, assume that the limit is the summation from n equals 1 to infinity. Obviously, if I wrote a limit, go with the limit I wrote. But since I didn't, assume n equals 1 to infinity. So what we have is the summation from n equals 1 to infinity of 1 over n to the 5. Is that going to converge or diverge? Well, that's pretty simple, isn't it? It's a p-series. P is 5. It's right there, 5. 5 is greater than 1. I really hope you know that. If you don't know that, you are not supposed to be watching this video. You've got a little bit of catching up to do on some very, very, very basic stuff. So, 5 is greater than 1. P equals 5. Therefore, guess what this sucker does? This sucker converges. Very simple, right? We'll do one more. The summation from n equals 1 to infinity of 4 over the square root of n. Well, that can be written as 4 times the summation of 1 over n to the 1/2. Well, summation of 1 over n to the 1/2, that's a p-series with p equals 1/2, which is less than 1, so it diverges. Pretty simple stuff, right? It will come in a lot of handy when we go over these next 2 tests, which will be the limit comparison test and the direct comparison test. So keep that in mind. Make sure you wrote some of that in your notes. Maybe you didn't even have to write it in your notes. It's very simple stuff. So just keep that in mind. We're going to move on to the direct comparison test, in which knowing about p-series will do you a lot of good. So, direct comparison test. What does the direct comparison test say? Well, it essentially says, if you have a series, we'll call it a sub n. If you have a series a sub n, so in this case, a sub n, it's the given series. In the case of the first example, a sub n would be 1 over 2 plus 3 to the n. It looks a lot like a geometric series, doesn't it? It looks a lot like 1 over 3 to the n, which would be geometric. but it's not. It's very similar, but it's not. What do you do with that? Well, before you just balled up and cried and gave up on the problem. Now it's going to be really easy though. Very, very simple way to do this. So you have the summation of a sub n. You want to compare it to something you know the convergence or divergence of, b sub n. In this case, what would it be? Well, obviously this looks a lot like 1 over 3 to the n. So you would want to make b sub n equal to 1 over 3 to the n. Essentially, what this comparison test says is if b sub n, or if a sub n is less than b sub n, so if your original function is less than the function you are comparing it to, and the function you are comparing it to you know converges, then your function converges. That makes sense, right? Because it's a smaller value than something that's already converging. Obviously, it's going to converge. The converse is also true. If a sub n is greater than b sub n, and you know that b sub n diverges, well, then a sub n is going to diverge with the same kind of logic. It's really a pretty simple idea, pretty simple concept. So let's put it into practice. It might be easier just to see it. I mean, I'm sure it is. I know it is. Seeing stuff is always easier than just reading or hearing about it. Although hearing about it is still usually easier than reading about it, at least for me. But let's analyze this one. So we've got the summation of 1 over quantity 2 plus 3 to the n. Like I said, that looks a lot like a geometric, but that plus 2 is throwing us off. So let's use the direct comparison test and get rid of it. 1 over 2 plus 3 to the n is less than 1 over 3 to the n, right? That just makes sense. Why does that make sense? Because that plus 2 in the denominator of a sub n makes the denominator bigger, which therefore makes the fraction as a whole smaller. You guys should know that. You know basic math. You can figure that one out. So 1 over 2 plus 3 to the n is less than 1 over 3 to the n for that reason. What does that tell us? Well, we know that 1 over 3 to the n is geometric with r equals 1/3, which is less than 1. Like I said, I hope you already know about geometric divergence and convergence. So then you should know 1 over 1/3 is less than 1. So the absolute value of r is less than 1. Therefore, this converges. Remember, a sub n, our given function, was smaller than a converging function. Therefore, it converges also. Does that make sense? I sure hope so, because I'm asking a rhetorical question. I can't, that's all I got to explain it. If it doesn't make sense, perhaps you should check out another video. But moving on to another example. So this one, the summation of 1 over n cubed plus 5n. Well, what does that look like? It kind of looks like 1 over n cubed, right? That's kind of what it looks like. 1 over n cubed would be a p-series. So let's compare it to that, because we know the convergence and divergence of p-series now. So that'll be a pretty easy comparison. So we're going to use the comparison test, and we are going to compare it to the summation of 1 over n cubed, which is a p-series with p equals 3, which is greater than 1, therefore it converges. Now we know the summation of 1 over n cubed plus 5n is going to be less than the summation of 1 over n cubed. Why do we know that? Because n is positive, therefore in a sub n, which is your original function, adding that 5n is going to make the denominator larger. If the denominator gets larger, the fraction as a whole gets smaller. Therefore, we know that summation of a sub n is less than that summation of b sub n. Therefore, we know, because b sub n converges and a sub n is less than it, we know that a sub n converges. So we know the summation of 1 over n cubed plus 5n converges. Pretty simple stuff. We're going to go into a slightly harder test this time. See, I even put asterisks by it. That means it's not easy stuff. So we've got the summation of 1 over 2 plus square root of n. So up until now, we've been doing very obvious comparisons, right? I mean, it's very obvious that you should compare this to 1 over n cubed. It's very obvious that you should compare this to 1 over 2 plus, or 1 over 3 to the n, rather. But this one seems obvious. The obvious choice is to just compare it to 1 over square root of n, right? Which would be a p-series with p equals 1/2, which is less than 1, therefore it diverges. So let's do that comparison. We know that 1 over 2 plus square root of n is less than 1 over square root of n, which is that p-series that we're comparing it to. That doesn't help us though. Why doesn't that help us? Well, because if it's less than a diverging series, we don't know anything, and that should make sense because the diverging series could be a wide variety of things. Saying it's less than a diverging series, maybe it converges, maybe it still diverges. Who knows? So this tells us nothing. As you can tell, I got frustrated in my notes. We don't know jack crap. Thanks, direct comparison test. Ha ha ha, I'm so funny. And then I freaking wrote quitty quitty. Wow, we're just gonna pretend that did not happen. Moving on. So let's not give up yet. Let's not quitty quitty, as I wrote in my notes. Let's compare it to something else. Let's see what works. So let's pretend we compare it to 1 over n squared. That is a p-series with p equals 2, which is greater than 1. Therefore, it converges. Unfortunately, though, we find out that 1 over 2 plus square root of n is greater than 1 over n squared. And yeah, that's just ugly. That's just an ugly little sucker right there, because that doesn't help us either. So finally, next, I should have written last, but I didn't know it would be the last one. We're gonna compare it to something else. Let's compare it to 1 over n, the summation of 1 over n. Well, what do we know about that? You should know by now. I didn't actually say this at the start. So if you don't know this, take note right here. The summation of 1 over n is a special case. It is harmonic, and it diverges. That is just something you gotta know. It saves you so much time. So, if that diverges, then what we need to be testing for is divergence. It needs to be greater than. A sub n needs to be greater than b sub n if b sub n is diverging. Otherwise, the test tells us nothing. So we write this down. Is 1 over 2 plus square root of n greater than 1 over n? Is that the case? If it is, then guess what? The test works, and we know that a sub n diverges. So let's find out. What would make that the case? It would be the case if 2 plus square root of n was less than or equal to n. Well, why? Because if the denominator is smaller, the fraction is bigger. We've talked about that several times. I hope you grasp that concept by now. So, you get this. You get 2 plus square root of n is less than or equal to n. So, move some stuff around. You get 0 is less than or equal to n minus n to the 1/2 minus 2. You can factor that. I know you guys can do basic math, so I'm not going to insult you. Basically, you find out that from n equals 4 on, from there on, it is larger. So from there on, 1 over 2 plus square root of n is indeed larger than 1 over n. Therefore, finally to that answer, the summation of 1 over 2 plus square root of n diverges because 1 over 2 plus square root of n is greater than 1 over n, which we know diverges. For n equals 4, it is greater than 1 over n. I should clarify that. So, there's a few examples of the direct comparison test. If you want to find more, I'm sure you can find some online, find some anywhere. There's so many places you can find it. Examples in your book, all that good stuff. But that is a brief overview of the direct comparison test. So lastly, we are going to move on to the limit comparison test, which I like even more than the direct comparison test. So the limit comparison test. The limit comparison test says this. If you have a function, a sub n, or a series rather, a sub n, and you know that it looks a lot like something. Just like the direct comparison test, you're going to find something that it resembles. If it resembles a geometric, try to find a geometric that fits it. If it resembles a p-series, try to find a p-series that fits it. So you're going to try to find something to compare it to. What does that test actually say? The test says, once you've found that comparison, b sub n, if the limit as n goes to infinity of a sub n over b sub n, I'll say that again because I can't write it, which is the downfall of doing notes like this. If the limit as n goes to infinity of a sub n, your original function, over b sub n, your new function, equals some constant c, a non-zero constant c, then either both of the series diverge or they both converge. That is a very useful test because hopefully you're comparing it to something you know the convergence or divergence of. So then literally if it gives you a number at all that is not zero or not infinity, then guess what? It either converges or diverges whatever b sub n does. Pretty simple stuff. So let's jump right into it. We've got the summation from n equals 1 to infinity of 2n plus 1 over quantity n plus 1 squared. So I wrote out a few of the terms, all that good stuff. It's always a good idea to do that, but sometimes I'm lazy and I just don't. So I wrote a note here because this is how I have to think about it. When n is large, the series acts like the summation of 2n over n squared. Why does it do that? Well, because as n becomes huge, that 1 becomes kind of irrelevant. Both of those 1s become kind of irrelevant. I think that's pretty self-explanatory as to why, because n is growing so big that 1 is just like there. It's not that important. So it starts to act like this. And that is equal to the summation of 2 over n. 2 over n is harmonic. Therefore, we know that it diverges. Good stuff, right? So let's compare. We know that 2 over n is greater than 1 over n. We're going to use 1 over n. We're going to compare it to 1 over n. You could also compare it to 2 over n. You're going to get essentially the same result. We're just doing that because 1 is easier to deal with, and we know that 2 over n is even greater than 1 over n. So it diverges. So we're going to compare them. So the limit as n goes to infinity of a sub n over b sub n equals the limit as n goes to infinity of a sub n was 2n plus 1 over quantity n plus 1 squared, and we're letting b sub n be 1 over n. Again, I emphasized you could let it be 2 over n, it wouldn't matter. 1 just makes it a little easier as far as the basic math of it. So, what does that become? Well, you do a little simplifying. I did that for you. I'm sure you guys can do that. You should get the limit as n goes to infinity of 2n squared plus n over n squared plus 2n plus 1. So now you got to cancel some stuff out. The way to do that would be to multiply by 1 over n squared on the top and the bottom. So I didn't write that in, but just imagine multiplying top, the numerator, and the denominator by 1 over n squared. You will get the limit as n goes to infinity of 2 plus 1 over n over 1 plus, obviously if you're multiplying by 1 over n squared, that becomes 2 over n, and that becomes 1 over n squared. What is that? Well, most of these go to 0. This goes to 0 right here, this goes to 0, and this goes to 0. Wow, that's fuzzy because I zoomed in so much. But the 2 and the 1 don't go to 0. So it just becomes 2 over 1, which equals 2. 2 is a constant. 2 is non-zero. 2 does not equal infinity. Therefore, it's going to act the same way as the summation of 1 over n. What does the summation of 1 over n do? Well, we know that diverges. Therefore, this series, the summation of 2n plus 1 over n plus 1 squared diverges by the limit comparison test. Yay! Happy day! Let's try. uno mas, and then we'll be done, I promise, because I have rambled long enough. So we've got the summation of 1 over 2 to the n minus 1. Well, what does that look like? It looks a little bit like the summation of 1 over 2 to the n. Actually, it looks a lot a bit like the summation of 1 over 2 to the n. I hope you can see that. You've just got to start realizing what the comparisons are. It's an acquired skill. The more you practice it, the easier it is to see the comparison you're going to need to make. And some of the comparisons you'll do are much more complicated than these. These are pretty basic examples. I'm just trying to cover the basics of the topic today. And then you can delve deeper into the more complicated comparisons. So we're going to compare it to the summation of 1 over 2n, which is the same as the summation of quantity 1 over 2 to the n. Obviously, that's geometric with the absolute value of r less than 1. Therefore, it converges. You guys should know how to do that. That's pretty simple stuff. So we're going to take the limit as n goes to infinity of our original over our comparison point. So we've got the limit as n goes to infinity of the original, 1 over 2n minus 1, over the new, 1 over 2 to the n. So that'll become the limit as n goes to infinity of 2 to the n over 2 to the n minus 1. Now what we're going to do here, I did not write this in. Man, I really should start writing more stuff in. I multiplied the top and the bottom by 1 over 2 to the n. So if you multiply the top and the bottom by 1 over 2 to the n, what do you get? You get, well, 2 to the n times 1 over 2 to the n. That's just 1. So both of those terms go to 1. And then you get, well, 1 times 1 over 2 to the n is 1 over 2 to the n. That's pretty obvious. So you get the limit as n goes to infinity of 1 over 1 minus 1 over 2 to the n. That's a mouthful. 1 over 2 to the n goes to 0. So you get 1 over 1. 1 over 1 equals 1, which is a number. And it doesn't equal 0. And it doesn't equal infinity. So our original function is going to act the exact same way as the summation of 1 over 2 to the n. 1 over 2 to the n converges. Therefore, our original function is going to converge. So the summation of 1 over 2 to the n minus 1 converges by limit comparison test because the summation of quantity 1 over 2 to the n converges. That is a quick overview of the direct comparison test, the limit comparison test, and finding convergence and divergence of p-series. I hope you found this video useful. I might be uploading some more stuff about more complicated topics later. I appreciate you watching this video. That's all I got. Bye-bye.